morning, everybody. Or I guess it's about to be afternoon. It's a beautiful day. How's everybody doing? Stability derivative says, where's Mom? Renee Estes, are you out there somewhere? Mom? LOCUS. That's right, that's the command. Are we going to be continuing 13C? You better believe we are. That's the plan. We're going to be continuing our Matlab script as well. So be ready. Matlab, you mean strictly worse Python? Matlab is nice if you have the license. Hello, Dark Shadow. But I told you about my crisis before. Oh my goodness! Renee D. Estes is here. My mom is in the house, learning control systems. I have an exam today. Can the whole class wish me luck? Hey, we wish you luck. Good luck on your exam. Anybody else have an exam today? You guys are going to do fantastic. You have this under control. Start in maybe another minute or so. All the best. Yes, all the best to you. No D rocks. You missed the proper response to hello there. Wait. My response? What was my response? Is it supposed to be yellow there? That's somewhere in the vet. Oh, General Kenobi. I don't know. I'm missing the beat here. Sorry. I know it's Star Wars. I know Kenobi, of course. I'm excited for the show. Let's bring on Obi-Wan. What do you say? Alright, I'm gonna turn down this music. I'm gonna get us started. Okay, let's do a super quick recap. We're working on an example, and we're gonna go up to right here. We're trying to control this plant, G. You can see it's a second order plant. We've just been controlling first order stuff so far, so this is a little more, it's a higher order system. And The starting point when making a controller is your performance requirements. So we have 3 of them right over here. 1, 2, and 3. The first 2 are transient performance constraints. You have to have an overshoot. I guess I put it equal to 0.163, settling time equal to 2 seconds. And then we have number 3, a steady state performance constraint. So KP being equal to infinity just means that if we give a step reference to this system over here, we want the output to follow that reference perfectly at steady state with 0 steady state error. So, Ace Slisher says sorry. What are you sorry for? You haven't even done anything. But I forgive you. So, given those performance constraints, we calculate the target closed loop poles, which that always starts by figuring out the continuous time roots, then converting them to discrete time roots because we're doing a digital control system. And so we said these are the target closed loop poles. What is that banging noise in the background? Is there a banging noise? It might have been the music. I turned it off. We also, wait, let me see if I totally turned it off. I think I did. Yeah, there's no noise. Sounds like an underwater drum. Did it turn off? An underwater drum? It sounds like we're in a fish tank and someone's tapping on it? What is going on? Do you still hear it? Good grief. You still hear... I wonder if it's this... What could it... Okay, what if I change... It could be like this fan behind me. What if I bring... I'm gonna bring this microphone closer to my face. And I'll put it on like this cardioid mode. Did I fix it? Sounds like the mic vibrating from the desk. There is a little fan. Okay, how about now? Sounds good now? It's gone? Okay. Let me back this off just a little bit. Maybe Annabelle is haunting you like in The Conjuring. I cannot watch horror movies anymore. I used to enjoy them, and now they freak me out. I tried to watch Hereditary recently, which is a fantastic film, but I couldn't even make it. I quit. Okay, guys. So it sounds like we fixed our sound issue. We're back on track. All right. So the root locus design technique is all about getting your closed loop poles to coincide with these target poles that you've chosen. So the first step, there's 2 criteria for the root locus method. The first one's the angle criteria. So I won't go through all the details here, but the angle criteria for us dictates that the angle contribution of our controller, so the angle of D evaluated at Z star, it has to be 51.3 degrees. If you need to contribute a positive angle, like we see here, positive 51.3, that means your controller needs a 0 in it because zeros contribute positive angles. Poles contribute negative. So we knew we needed a 0, but the problem is, well, we explored it over here. Like if your controller just has a 0, it will be an acausal controller. It'll depend on error values from the future, which we kind of proved here. Like it depends on an error from one time step in the future, which we can't get. So you always have to have at least the same number of poles as you have zeros. So if we have 1 0, we need 1 pole. So what we did is we said, we know we have to contribute a positive angle, but you can't just have a 0. So we added a pole. And this is where we ended up last time. We said, look, D still needs to contribute positive 51 degrees, but we're doing it with a 0 and a pole. And the thing is, there's an infinite number of combinations of zeros and poles you can pick to get this overall angle contribution of 51 degrees. And you're going to find that you have the same sort of issue on homework 6. So we're going to talk about how you navigate this issue of having a bunch of different options. So really, there's no way around having to iterate on your control design process and look at a bunch of different possible controllers and pick the one you like. This is one drawback of the root locus method, that it kind of lends itself to an iterative approach. It's not like you can design a controller in one shot with this root locus design. So we're going to cycle through the range of possible controllers. We're not going to go through all of the infinite possibilities, but we're going to sample a set of controllers that might work, and then we're going to whittle it down, pick the one we want. So, all right. Let's just think about this for a second, like intuitively. Overall, d of z needs to be 51.3 degrees. The angle contribution of a 0 is going to be a positive number greater than 0. And the angle contribution of a pole is always going to be less than 0. So if I know that this number is greater than 0, this number is less than 0, and overall it has to be positive 51.3 degrees, we can start to define the smallest possible angle contribution of the 0 and the largest. And then we can like pick controllers in between those angle ranges. So, and this kind of goes to the question I think we see in the chat. Maybe I'll put this right here. I'll make 2 points. So a 0 can contribute positive 0 to 180 degrees, somewhere in between there. It can't contribute more or less than that. A pole can contribute between minus and 0, 180 degrees. The way to visualize this, I'm going to kind of go off the page. And I'm going to show you over here. So remember, we have a graphical technique for evaluating the angle contribution of something. So let's put this in the complex plane. I'm going to throw some z star in here. This is a target pole. And let's say I want to evaluate the angle that a 0 makes with respect to this pole. So let's just put a 0 right here. The way to evaluate the angle is first you draw a ray from the 0 through that target pole. And then you find the angle from the positive real axis over to that ray. And then this would be the angle contribution of that 0. So you can see, let's imagine that. So I want to explain why we can only have like between 0 and 180. What if I move this 0 way out here? You can see that if I draw a ray, once again, close enough, this angle gets steeper and steeper. If I move this angle all the way out to like infinity, the angle that gets made is going to be close to 180 degrees. Angle approaches positive 180. And same thing, if this was a pole, we can calculate the angle in the same way using this technique, but when it's a pole, you have to make the angle negative. So if I move a pole further and further and further to positive infinity, relative to some z star, that angle is going to go to minus 180. Now, imagine the other side. If you move the 0, maybe I'll even do a different color. As I move the 0 this way, the angle is going to get smaller because I'm going to draw this ray. I'm going to do the same thing. I go from the positive real axis counterclockwise. So that angle is getting smaller. And if I move this 0 towards minus infinity, the angle is going to approach 0. Angle approaches 0 degrees. And if it's a pole, same thing. It's going to trend towards 0 degrees. All right, so a pole or a 0 can only be plus or minus 180. That's the full range. And I want us to keep that in mind. I know I'm scrolling away from that. Hopefully you've had a chance to sketch that. So when we look at this, it has to be positive 51.3. And the smallest angle contribution that the pole can give us is 0 degrees. Like, it's going to give us between 0 and minus 180, so it's always going to be subtracting something. So that means the smallest angle that the 0 can contribute is 51.3 degrees. Because if the pole is anywhere, it's going to subtract something. So the smallest possible angle from the 0 is 51.3 degrees. So let's write that down. Smallest possible angle for our 0 is 51.3 degrees. The largest we're not going to do this, but we could make it 180 degrees. If I moved the 0 all the way to positive infinity, I'm going to make an angle of 180. And this will imply that the pole is going to have to subtract like close to 130 degrees to bring the overall angle back to 51.3. But that's possible. Tropical Geek, non-student viewer here. Which math is this? This is a control systems course. I don't know what math you would call it. Maybe somebody in chat has an opinion. Difference equations? Differential equations? System dynamics? Does it matter if it's positive or negative 51.3 degrees in the end? It has to be positive. I'd call it mechanical engineering, Tropical Geek. Actually, it doesn't have to be mechanical. Mechanical engineering, yeah. Okay. So what I want to do is I have these limits, and let's make a table because this kind of forms the boundary of possible controllers we can try. So I'm going to make a table with 2 rows, and this row is going to be the angle contribution of the 0, z star, minus z1. And then this is going to be the corresponding pole. And so the smallest angle contribution that I can give from the 0 is 51.3 degrees. And the biggest, let's put it like here at the end of the table, is 180 degrees. And we can figure out the angle that the pole has to contribute from, well, from this equation up here. So right, the angle from the pole is 51.3 degrees minus whatever is from the 0. So we're going to do, well, this means the pole has to contribute 0 degrees in this case. And in this case, it's 180 degrees minus 51.3 degrees, which is 128.7. And then in between here, we can have, a bunch of different possible angles from the 0. Let's say like 75 degrees is somewhere in the middle, or actually it's not really to the middle of it. Maybe it should be in the second. I don't know. But it's in between. And we could figure out what the angle of the pole needs to be. All right. So from the angles, we can determine where the actual poles are located on the real axis. So what I want to do is we're going to move on to this. How can I calculate the pole and 0 locations based on these angles we have in the table? Because this doesn't, just knowing the angle, we're going to need to know where the pole or 0 actually is. And so I want to create a formula that we can just throw into Matlab so that we don't have to do this calculation by hand each time. So come down here with me. We're going to draw the complex plane again. And we're going to make a generic formula for, based on an angle, finding where a pole is, or 0. So let's first throw just a generic z star in the complex plane. And this z star, it has a real part, it has an imaginary part. So I'm going to draw a line down to the real axis, and where it intersects the real axis, this is where z is equal to the real part of z star. Okay. And let's say I know the angle that I want to make with z star. Like from this table, let's say I have a 0 and I know I want it to make 75 degrees. So that 75 degrees, it's going to come from the ray that goes down to the real axis and intersects here. So in this case, I kind of drew it to be something like 75 degrees, but this is going to work in general. So I'm just going to call it theta, because it doesn't matter if it's 75 degrees. And what I'm looking for is, so I already know the angle, but what is the z location down here on the real axis? So that's what we're trying to solve for and get a formula for. So the way that I'm going to do this is I'm going to make a coordinate that starts at the real part of z star and it goes back this way in the negative real direction towards wherever our 0 or pole is going to be. And I'll just call this x. So the origin of this coordinate is at the real part of z star, and then it works its way in the negative real direction. Okay. So that would mean if we could solve for what x is, then that means this z location, which, I called it a question mark. Let's just call it z1. Use arctan. Yes. We're going to use a tangent here. So the formula for z1 is the real part of z star minus x. So if we can figure out what x is, we'll subtract it from here, and that'll bring us over to z1. So we have to figure out what x is here. So the way that I've made this coordinate, x is, it's positive in this orientation right here. But we can just use trig, because I know the angle in this triangle, it's theta. I know this height. This height is the imaginary part of z star. So it goes down from 0 up to here. So that means, as A. Slisher said, the tangent of whatever angle it is the imaginary part of z star divided by x. So I guess we don't have to use arctangent. We can just use tangent here. So that means x is the imaginary part of z star divided by the tangent of theta. So if theta is 75 degrees, you plug that in there. Okay. And so we're just going to plug this into our equation for z1. So the location of this unknown 0 is the real part of z star minus the imaginary part of z star divided by the tangent of that angle theta. Now, the nice thing about this formula is, let's say your angle is smaller than 90 degrees. So like, or I mean, it's bigger than 90 degrees. That means you're somewhere like over here. So I don't know. Let's say we had that theta, and I'm trying to find the location of a 0 over here. When you use this formula, like you'll notice that I'm going to have a negative x because I'm not going leftwards anymore. I'm moving to the right. This formula will automatically, the sign of this term will change, and it still works. So it's really nice. So this is just something we can throw into Matlab. Given an angle of a 0 we want, given that we'll know the real and imaginary parts of z star, we can just figure out where the 0 is. Now, if we have a pole, we know that poles contribute a negative angle. We could use this same formula, but we'd have to, when you put in theta, you'll put the negative, you'll still put the positive angle. That doesn't make sense when I'm saying that right now. But like if let's say you're looking for the location of a pole, and I know a pole is going to contribute, let's make up minus 45 degrees. You could use this same formula, but instead of inputting negative 45 here, you would put positive 45. So maybe we'll come back to that, but tuck that away. This still works for a pole. You just have to make a small adjustment. So direction of angle doesn't matter. I wouldn't say that necessarily. We'll come back to it. All right, so let's run with this example of 75 degrees. So we'll use this formula to figure out where the 0 location is, and I'm going to go over to Matlab to do this. Let's go over here. This is a code we started last time. Maybe we'll just run it really quick. Oh, what did I do? Oh, I cut out too much. So fs was... We just have to plug this in real quick. It was 5. That's the sampling frequency. The period is 1 divided by the sampling frequency. Okay, now we have, I think. Okay, so yeah, like the angle of D was 51 degrees. So what I'm going to do, and we'll modify this code, but we're going to go through a bunch of different controllers, and let's say angle Z1 that we're testing right now, and I'll say this is degrees, whatever. Let's say it's 75 degrees. So the location of Z1, based on this, we can use this formula. I take the real part of Z star, I subtract the imaginary part of Z star, and I divide by the tangent of the angle, and we have to do tan D if I'm putting this in degrees. So how about why don't I just run that really quick? And this spits out Z1 is located at 0.4. So if it's right there, it's going to contribute 75 degrees that I need. So let's do the pole. So this will come back to my earlier statement about like what do you do for the pole location. So first let's get the angle. So if we go back to the notes really quick, the angle of the pole, which is in the second row of this column, you take you take the angle of the 0 and we have to subtract 51.3 degrees. So we're going to do the same thing. So it's going to be angle Z1, and then that 51.3, it came from this variable. So if we run this is going to tell us the angle of the pole, which will be some negative number. Or wait. Angle Z1. Wait. Oh, I reversed it. It's supposed to be angle D. Sorry, I had the order reversed. This should be a negative number. The pole has to contribute a negative angle. So let's run that again. Minus 23 degrees. Okay. So the pole has to contribute minus 23 to bring us back to that 51 degrees, whatever. So where's the pole going to be? We can use this same formula. But we have to make a change here. So P1, the location of the pole, you need to do the negative of the angle of the pole. So we'll change this to P1. Okay, this is the change that I'm talking about. So I run this, and P1 is located at minus 0.4579. Okay. Let's go back. Let's go back here really quick. So I'll put this right here. If angle of Z star minus Z1 is 75 degrees, then here's the formula for our controller. It's going to be some gain And then it's going to be z minus the 0 location. So z1 was located at 0.4011. And then the pole was located at, so we have to subtract minus 0.4579, which will just be z plus 0.4579 in the denominator. Let's test this really quick in Matlab and verify that this satisfies the angle criterion, which is the whole point of this. So I'm going to input this specific controller. Okay, so we'll say D, and I'm calling it no K because I don't know what the gain is yet, and I'm not gonna put that in there. So I'm gonna say it's a transfer function. The numerator is Z minus Z1. So I guess I put this here. And then the denominator is Z minus P1. And then to make it a discrete time transfer function, we just add the sampling period at the end. Let's evaluate this. Let's take a peek at it. And okay, so I want to quickly verify the angle criterion, which is we take G, which we defined up above, we multiply it with D, and it doesn't matter if we don't have the K yet, because the K doesn't contribute to the angle anyways. We have to evaluate this. So we use eval FR. We evaluate it at Z star. And then we take the angle of it. And this angle should overall evaluate to 180 degrees. So let's run that. Okay. This gives us negative 3.14, which is negative pi. The angle of negative pi is the same as the angle of positive pi. It's like turning around 180 or minus 180. It brings you to the same angle. So I'm not worried about this. That's okay. So this controller works. We've satisfied the angle criterion. Let's go all the way with this controller. You're getting positive? Oh, that's great. Is anybody else getting positive? I mean, like I said, it doesn't really make a difference. Same angle. Let's go back here. What I want to do, you got 2.13. Don't say that to me. All right. Let's figure out what K is. The way that you figure out what K is we have to use the magnitude criterion. So this is the second criterion for root locus. You take G times D, you evaluate it at Z star, you take the magnitude of it, and it has to be equal to 1. And we've shown a couple times how we get the gain from this. So I'm just going to go to Matlab, and we're going to calculate it. So the gain, which I'll call K, I have to take G times D without the K. Once again, we have to evaluate it at Z star. And then we have to take the absolute value of that, which is the magnitude. And then we have to do 1 divided by that whole thing. And this is going to give us our controller gain so that it satisfies the magnitude criterion. And then that'll allow us to put together our full controller, which would just be K times D with no K, which just brings us back to D. All right. Okay. Why don't we run this really quick? Let's see what D is. What was, so K was, ooh. We've never gotten a K that big. 27. And, okay. So this is our controller. Now I want to look at where the closed loop poles of this system are. So we'll make the closed loop transfer function. Remember, it's G times D divided by 1 plus G times D. And to simplify it, we use the min real command. All that does is simplify this. So let's run it. Okay. And here's something I wanted to point out to you, and this is why we have to iterate on this controller. This is a third order system. You can tell because the denominator is a third order polynomial. But we only specified 2 closed loop poles that we wanted, right? Like Z star is a pair of complex conjugate poles. So this is cubic, meaning there's going to be an extra root which we didn't explicitly specify. So let's figure out what it is. So we use the pole command to figure out what the closed loop poles are. And there's going to be 3 of them. So these first 2, these are the ones we specified. These are equal to Z star. Like if you want to check, our Z star variable should be the same. Boom. That's good. This is the third closed loop pole. And it's on the negative real axis. And it's a purely real root, but we know that a root on the negative real axis has some unfavorable behavior, like it creates this like sawtooth signal. Is this at Matlab? Yes, it is. It is. And for some of these controllers, like I randomly picked 75 degrees for the 0. Some combinations of zeros result in the third pole being unstable. And so what I'm trying to say is you don't know what this is going to be until you run these calculations. And the first one that you pick might be bad. It might be an unstable pole. Remember, even if we achieve these target poles with 2 of our roots, if a system has 1 unstable root, the whole system is unstable. It just takes 1 bad egg. So there's no way to know what this is going to be unless we check. And so we have to iterate on a bunch of controllers. So what I want to do, so we went through this one process right here. It all started here. I specified the angle of the 0. And then following that, it just followed a deterministic line all the way to our closed loop controller. What I want to do, and this is what you need to do for the homework, in my opinion. Yeah, this is what you're going to have to do anyways. You need to make a loop that cycles through different possible angles. And this is why we earlier on defined what's the smallest possible angle, what's the biggest possible angle. So let's modify this code a little bit. What I'm going to do is maybe I'll copy this, comment it out because I want to like preserve it, But we're going to go down here and do the same thing, but we're going to make this like an iterative thing. So here we go. Let's say instead of specifying one angle for the 0, I'm going to specify a bunch of them. And I'm going to put them between the smallest and largest angles that we know it can be. So the smallest the angle could have been was this, actually. 51.3 degrees is angle D. So I'm going to put that here at the bottom range. And then at the top range, it's 180. And linspace lets you choose how many points in between you want to choose. So let's try like 10 different controllers. And we're going to have Matlab do the work of going through here. Okay. Actually, let's make this is what I like to do. I make a variable number of controllers. But there might be multiple feasible solutions. Shouldn't we use an objective to make it unambiguous which one is best and which we should use? So you make a good point that if I just pick 2 target closed loop poles, it doesn't really in the end, I'm still going to have a bunch of controllers that do a good job. And I think what Freeman's getting at is like, how do I choose between a bunch of feasible controllers? Well, you can make an objective function like with LQR that chooses an optimal one, but we'll get to that later. Not today. For now, we're just going to be satisfied with having a bunch of feasible ones, and we kind of just loosey-goosey pick the one we like. Okay. So I'm making 10 possible controllers. I define 10 possible angles between these limits. And actually, it's better to make a buffer here. So what I mean by a buffer is you shouldn't pick the smallest and the largest, because the smallest and largest imply a pole or a 0 exists at infinity, which can result in some problems. So like, I like to put, let's not go with the very smallest. Let's add like 10 degrees. And same thing at the top. Let's not go to the very max. Let's go to like the max minus 10 degrees or something. So we're not totally exploring the full space. Okay. So this is going to be a vector of 10. This will create 10 possible poles. And here's where I'm going to do a for loop right after that. So I'm going to say like for, let's do like j equals 1 to the number of controllers. And then I'm going to put an end down here. So basically we're going to cycle through all of this stuff. But we have to make some changes here. And I know we're already close to the time that this lecture is over. But let's try to do it. So we have to make an index for each of these. And over here in this formula, we have to pick the proper angle of the 0. So like I should pick the jth 0 angle, the jth pole. And here we go. For transfer functions in Matlab, you can also create a vector of transfer functions. So this will be the jth index of D. And so basically, I'm just going to blast through this. We have to add indices to a bunch of these. This was just checking the angle. We don't really need to do that in here. We need to calculate the gain. We have to make sure it's with respect to the jth controller here. So I put that index. Then we have our jth controller. So basically, you need to add an index to anything that's changing with this loop. G doesn't need an index because the plant is always the same. And wait, let's just see if this runs really quick. I want to make sure there's no error. So all I did, I put a for loop. I put indices around here. So it's doing this operation a bunch of times. Okay. So I didn't suppress things with a semicolon, so it's like spitting out all of these controllers. So like if I want to access the first controller we made, it's D1, D2. You see like these are changing. So some of these controllers are not going to be good. So the way you can check, we want to look at the closed loop polls. So like let's look at the polls for the first controller we made. So I made 10 closed loop controllers. Let's look at the polls from the first controller. What are we making? We're making a controller. This is unstable. Look at this. 2 of these roots are located at Z star. That's great. But our third closed loop pole is on the negative real axis, and it's outside of the unit circle. You get a different answer? Do other people get the same answer? If people are getting the same answer, then then that's good. If nobody's getting the same, but I think this is right. Same answer, okay. Let's look at the second controller. Okay, this one's at least stable, but this root is on the negative real axis. So what you can do in your loop, you could even add the calculation of the poles as part of the loop. Okay, so like I said, on homework 6, the same thing's going to happen to you. You're going to have a bunch of different possibilities, and you have to kind of iterate through and then pick a controller that's good. So what I want to do is give you some guidelines for deciding what's a reasonable controller. So let's go back over here. Okay, so yeah, so I pose this, like, what's the difference between these controllers? Don't they all achieve the desired closed loop poles? Yes, they give us the 2 desired closed loop poles, but the problem is they give us an extra pole that we didn't explicitly account for. So all this is saying is, you see like 3 Z terms here. It's third order, so there's going to be 3 roots. So we've already seen this. But I think down here, I made like, okay, what we have to watch out for. The biggest thing is the third closed loop pole unstable? Okay, we need it to be stable. If one root is negative in the real portion, making it unstable, does the whole system... Well, if the real part is negative, that doesn't necessarily make it unstable. If the magnitude of the root is outside of the unit circle, then it's unstable. So, unstable means magnitude outside unit circle. If that's the case, the whole system is unstable. If you have one unstable pole, everything's unstable. Okay, another thing you have to watch out for, and we'll have to talk about this more after spring break, does the third pole dominate Z star? So dominate is a technical term in controls, meaning that, well, I'll just give the definition. The slowest root of a system is the dominant root. We call it the dominant root because the slowest root bottlenecks the performance. So, like, let's say I want a settling time of like 1 second for my system. and I choose Z star to achieve that settling time. If my third closed loop pole has a settling time of like 5 seconds, well, now the overall system is only as fast as the slowest pole. So that's why you have to watch out for, so does third pole dominate Z star? What you have to check for is its magnitude greater than the magnitude of Z star. Because we know in discrete time systems, the speed of the root is directly related to its magnitude. The farther away you are from the origin, the slower you are. So if the third pole is farther away from the origin than Z star, it's going to be slower. It's going to dominate your system performance. Okay, one last thing, and then we're closing. Is the third pole on negative real axis? And this isn't always bad. We know that having a pole on the negative real axis for a discrete time system creates a sawtooth-like response. Something like this, which is undesirable usually. But if that root decays really fast, like if it's on the negative real axis but it's close to the origin, then that means its dynamics die out really fast, and we won't really see a lot of this in the response. So actually, like 2 and 3 are kind of related. I guess 3 is a special case of 2 here. As long as a root on the negative real axis doesn't dominate your target poles, if it's not slower than them, then you probably won't even see it very much in the response. But it's still something to watch out for because it might mess with your overshoot and stuff like that. Okay. So I think I got through the stuff I wanted to today, like showing you a way to iterate on your control system design. Freeman says, if feasible, is a root at 0 plus 0j always preferable? So that's putting a pole right at the origin, meaning it decays in one step. That's a good question. That would mean that it doesn't dominate the other poles ever. That's a great question. Sometimes moving a pole to the origin results in more control effort being expended. And so it might take more energy from your system to do that. Digital Controls Freak says, if a root is in the left half plane but not on the negative real axis, does it still have a sawtooth response? No, it doesn't. Ace Lisher says, isn't a pole at the origin non-existent? No. It exists. It'll result in a 1 over z term. Zach says, can you go back to the code and show the for loop again? Yeah, let's bump over there. And then we're going to start the 334 lecture. We're having a back-to-back class. That's going to start at 1 p.m. So, yeah, this is a way to iterate on that. Okay, people. I'm going to step away from the stream for like a minute or two, and then I'm going to boot it back up, and we're going to get into the MAE 334 content. So you can hang around or whatever. Have a great spring break. Please do. Is there a reason why you're not using the notebook functionality, aka Matlab Live Editor? There's no specific reason. I'm just not as familiar with the live editor, and that's probably why. just not being familiar with it. Hey, have a good day, everybody. All right. See you guys soon. You can throw questions in Discord and so on. Hey, see you guys. Peace, peace, peace. Hello, 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 hello. Okay, we're going to start the 334 lecture. Are people from 334 here? Are you with us today? Okay, cool. We got Julie, the penguin, sinking Halo. Yub Yub Commander. I like that name. Oy. Well, I hope you guys are ready for spring break. It'll be nice to get a little reprieve from school. I hope you can get some rest. Glory. I know. A well-deserved break for everybody. Very well deserved. Okay. How about we get started here? We'll get right into it. I'll turn this volume down. Let's do that. Okay. And so basically I want this to be, I'm listening in from Germany. Of course that's fine. What am I doing in the break? I'm going to rest a little bit. I'm going to go for a nice run, a couple nice runs in the sunshine, if the weather next week is as beautiful as it is this week. I'm not going anywhere. I'm going to stay in Buffalo. I'm just going to chill, try to catch up on some things, catch up on sleep and so on. Okay, so I have, the goal of this is to talk about some of the concepts behind Lab 2. It's our second lab experiment, and that's what you're going to be doing when you come back from spring break. So what the lab, actually I'll motivate it first, and then I'll tell you what exactly it is. But it's all about an experimental way of getting a dynamic model for a system. And I thought I want to contrast this experimental way of getting a model with the way that we model things in the dynamic systems course here at UB. So in MAE 340, you guys did some modeling of like mechanical systems, electrical systems, so on. And the approach we use there is not the approach we always have to use. Okay, so why do we use mathematical models in the first place? And here's two reasons, in my opinion. The first being prediction. If you can model something, model a process with math, you can predict the future, right? I mean, that's what weather is about. Can you identify nonlinear dynamics using the step response? It's a great question. It's what I'm going to show today. When you do a step response, you're looking for specific characteristics. For a nonlinear system, you don't know the parameterization of that. We'll just let it go. Okay, prediction number one. Like, think of modeling the weather. Actually, I was listening to the radio the other day. They're putting up like an unprecedented amount of like weather stations out in like the Midwest to improve our ability to predict extreme weather events, tornadoes, and so on. But speaking of nonlinear models, that's what our weather forecasting models are. They're these crazy nonlinear partial differential equations that depend on your barometric pressure, your temperature, blah, 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 blah. But prediction. And then control is the second purpose. Because, I mean, if you can predict how something responds to excitations, you can then control that thing. So I'm not saying, well, I guess coming back to the weather, wouldn't that be the goal? If we could control weather, I mean, that's kind of what climate science is trying to do by suppressing greenhouse gases and so on and so forth. That's a more complex model. Bringing it more back to our applications, I want to talk about DC motors. So we'll use that as an example today. Like DC motors are found in all sorts of applications. I love to use DC motors for balancing robots. I think I showed you guys a couple of those before. I have one right here. But yeah, just the basic idea, it's balancing on two wheels. Actually, I'm using stepper motors here. But if you want to build a system like this, you have to have a model for how the motor responds to voltage. How does the angular velocity of the motor change when you apply voltage? And so you can do more. You can do cool applications like that. But you need a model for it to work. So what we've done so far in this class is we've done calibration, which is a type of modeling, but I'm going to distinguish it from the type of modeling that I'm talking about today. Calibration is a steady state model. I'm an electronics engineering technician course, and we are learning about DC motors right now. Oh, sweet. Okay, this is perfect then. So calibration is a steady state mathematical model. Let me explain with this, because we've done calibration of a DC motor recently, but it was just a steady state calibration. So I'm trying to get this all in the frame. Spool out a little bit. Okay, so we've worked with 2 DC motors in this class. We have the little hobby motor that comes in your kit, and then this past week we worked with like a slightly larger motor. But the principle is the same, that you provide some voltage, and we're doing that by specifying the duty cycle, and we can command that with the Arduino. And we've been looking at what's the steady state angular velocity that results. So what I mean is the effective voltage, like maybe we have everything turned off, and then at some time t0, you activate the voltage. And the motor, it's going to respond, and at t0, right when you turn on the voltage, and you might have noticed this last week, you don't immediately just go to a steady state speed. There's this exponential transition. Like first the motor like speeds up really quick, and then it starts to slowly approach the steady state angular velocity. And this steady state angular velocity is what you measured in the workshop. It's what you're measuring with our first assignment that's due tonight. Don't forget about it. But this is the steady state angular velocity. It's the angular velocity that we're approaching. Okay, so what I want to point out is that calibration, what we've been doing, it doesn't capture the transient dynamics. So transient dynamics are the dynamics that happen in transition to the steady state condition. So these dynamics, so like let's say we settle like around here. Like at this point, we've basically reached the steady state value. Everything between t0 and that settling time, we call that transient dynamics, because they don't last. Okay, so calibration doesn't capture the transient dynamics. So is it important to know the transient dynamics? Yes. Well, depending on your application. But in general, for controls applications, like that little balancing robot, aircraft, so on, you do need to know those transient dynamics characteristics. To capture transient dynamics, you need a dynamic model. What do we mean by a dynamic model? Well, it's everyone's favorite math, differential equations. How do you guys feel about differential equations at this point in your academic career? I know when you first take the class, like sophomore year or something, it's like, oh my God, what is this magic? But I hope they become your friend. You're over it? Come on, Julie, you love differential equations. I know it. Okay, so an ODE to ODE, an ode, I get it, an ode to ODEs. Yes. All right, so you need to have a dynamic model, which is a differential equation. So I want to contrast our dynamic systems approach. What I mean by this is what we learn in our MAE 340 class versus the experimental approach that I'm going to talk about today. So this dynamic systems approach, and now we're going to go off the map here. This is using physics or first principles. So what I mean by this, if you're going to model a DC motor using first principles, so you might have done something like this in dynamic systems. So we know that a motor is an electromechanical system. So it has an electrical part, which the electrical part of a motor, we typically model it with a resistor. It has some inductance. So like we'll have R for the resistor, L for the inductance. And this interfaces with the mechanical part. So I'm going to put like a little like circle over here. And what this represents is a transduction process. Like in MAE 340, we call it a transducer. A transducer just transforms one thing into another thing. So we have a voltage here on this circuit. It's going to transform into a torque that acts on a rotor. So I'm just going to kind of draw like just some inertial thing over here. And this is going to rotate. So maybe it has an angle theta at any time, but it also has an angular velocity theta dot. So this is our rotor of the motor. So the rotor is just the spinning part of a motor. So yeah, you provide some voltage and it's transduced into a torque that acts on this. And we know that, okay, we can analyze using Kirchhoff's laws. We have some current running through here, and I'm just going to write this out really quick. If you go through all the steps, you get a second order transfer function for the speed of the motor. Actually, so let's put, actually I'll call omega the speed of the motor, and let's put it in the Laplace domain. If you don't like differential equations, you definitely don't like the Laplace domain. But this is just a truncated way of writing this model. But we have like some torque constant. I didn't even, this is part of the transducer, by the way. But I'm just writing this out to make an example. So J, this is the inertia of the motor. I just want to make the point that you could go through Newton's laws, you could go through Kirchhoff's loop and voltage rules and so on. This is just another constant for the motor. But you get a second order linear system. And a transfer function is a differential equation just in a different form. You can convert back and forth. And this is a totally valid way, of course, to model a motor. But I want to point out some weaknesses. So let's say that I want this model to describe a real life motor, like that I have sitting on my desk. Maybe this one right here. If I want to use this differential equation, if the step response of this system in the theta component is unbounded, yes, but not in theta dot. Theta dot will go to some steady state value. I would need to find the inertia of the rotor in here. Well, the rotor's sticking out over here, but it's embedded in the motor. I'd have to get the resistance, the inductance. I'd have to get these torque constants. So the point is, if you want to use this type of model for this motor, you have to get all of the parameters in this model. And they're not easy to get. It's not easy. You'd have to like disassemble this motor, I'm imagining, to like get the rotor out, and it's just these kinds of models, you can get them on paper, but when it comes to using it to describe a real life system, you need all the parameters, and they're hard to get. So we have an alternative way of getting a model. And it's based on using experiments. I mean, you'd have to use experiments to get these parameters anyways, and use this modeling approach. But I'm talking about a different type of experiment that directly gives you a model without having to measure these specific parameters. Okay. So there is an alternative modeling approach or philosophy, and it's called system identification. And like I said, this approach doesn't care about all of these specific physical parameters in here. So sometimes we call it black box modeling, because it's like we look at the system as this box. I don't see the inner workings of it. I don't care. I just want, in the end, a model that expresses the relationship between the inputs and outputs of the system. Okay, so let's describe this approach. Okay. So we'll say like system ID aims to establish input output relationships for a system, and these are dynamic relationships. It's going to be a dynamic model without bothering with physics. Okay, so we're going to do a simple example of this, and this is what you're going to do in your second lab. There's many system identification approaches. Some of them are like very automated. It's like using a toolbox and a software to just look at a bunch of inputs and outputs and create essentially a curve fit and give you a model. So let's apply this to the DC motor, or let's apply one approach. So the DC motor, I apply a voltage. So I'm going to have like the input over here on the left. It's the voltage. And we're going to have the output, let's just say angular velocity. And if I apply a step voltage like this, we know that the angular velocity, it looks something like this. Now, system identification looks at this relationship and it says, I don't care about the physics. I care about what is a mathematical function that can fit a response like this. And really, even though the underlying physics might be third order or second order or whatever, this looks like a first order response. It looks like a first order response. So we can probably fit it pretty well with just a first order function, a first order dynamic system. So let's just try to fit it with a first order system. So for a lot of system identification approaches, you at least have to assume an order of the system. And so we're going to assume a first order. Okay. The defining characteristic of a first order response is the time constant. Does anybody remember the definition of the time constant? Defining characteristic of a first order system is the time constant. I want to show you a way to get the time constant. The time constant, first I'll show you what it means. So you can see that the angular velocity is approaching some steady state value here, right? The time constant is the time it takes to get 63 point, what is it? I think 63.2. Let's just call it 63%. The time it takes to get 63% closer to that steady state value. So we'll say that amplitude is y steady state. And we started our response right here. And 63% of that, I don't know, it's like once we get here. So the time it takes to go from 0 up to that 63% value, we call that tau, the time constant. So if you know the time constant of a first order system, you're basically set. So a first order transfer function, so let's say we have omega, the speed of the motor. I'm going to make a transfer function related to the incoming voltage. I'm just going to presuppose a first order relationship. It's equal to, let's put it over here. S plus 1 over the time constant, and then there'll have to be some gain in the numerator. But let's not even worry about that for now. This right here is a first order transfer function. So yeah, there's two key parameters, the time constant and the gain. Derivative at the moment after the step defines a line which intersects the steady state line, the time of that intersection, since the time step is the time constant. I don't know what you're saying, Freeman. Okay. I'm going to show you a way to estimate the time constant. I'm going to go over to Matlab because I have some data here, because you're going to be analyzing this kind of data in Matlab. So I want to show you a technique in Matlab. Let's go over here. Okay. We're going over here. I'm going over to Matlab. And here I have a graph. And this is supposed to represent some experiment. Yeah, maybe it's a motor speeding up. And like any real life experiment, there's going to be noise in the data. And that's why this looks all fuzzy. So let's assume that this is the angular velocity of a motor, and let's say it's in radians per second. So we start at minus 15 radians per second. So that means the motor's actually spinning one way in a certain direction. And then it speeds up to 15 radians per second. So it starts spinning the opposite way. So this is like an alternating rotation. And I want to get the time constant here. So one way is to just eyeball it. It's not ideal. Let's zoom in here. We start at minus 15. We go up to 15. So if we make 63% of the progress to get there, well, we're changing by an amplitude of 30 because we're going from minus 15 to 15. So if I take 30 times 0.63, that would be 63% of the way, but I have to add this to minus 15 where we started. So by the time we get to 3.9, that should be the time constant, right? Wait, is that right? It's 15. I guess that's right. And okay, let's kind of just use our cursor. And this is not the ideal way to do this, by the way. I'm going to show you a better way. But I do this to show you the difficulty of using such a technique first. Oh, in Germany you define it a bit different, but it's an equivalent definition. Okay. Let's say it's around half a second, though, because we started going up at time equals 1, and then around time equals 1.5, it seems like we're kind of there. So it takes half a second to get 63% of the way up. All right, so I'm going to go back over here. So we're looking at a set of data. Let's just call this an example. From visual inspection of noisy data, not an ideal approach. I would say tau is approximately 0.5 seconds. Okay. This is not ideal because as you've witnessed this process, it's just what I just did, it cannot be very accurate. Let's look at a more accurate technique. And this is basically what I want to show you today. A more accurate technique for getting tau. This is called the error fraction method. Okay. So first thing is, we assumed that our system is first order. And a first order system, just scrolling to something really quick, it's going to have a response like this. So let's put this in time. Omega as a function of time, the angular velocity of this motor, it's going to be the steady state value that it reaches. So in our case, it got up to like 15 radians per second. Plus the initial value minus the steady state value. So initially we were at like minus 15 radians per second. You multiply this by e to the minus t over tau. And we're trying to figure out tau. Okay. So what I want to do is I want to solve for tau. Can you put the plot on the screen again for a few moments? I'll be right back to it pretty quick. So I'm going to isolate this exponential term by itself first. E to the minus t over tau. That would be the angular velocity as a function of time. You subtract this steady state value. And then we have to divide by our initial angular velocity divided by subtracting our steady state. So all I did was isolate this exponential term. Now, this term on the right-hand side, this is the error fraction. And we refer to it as like gamma as a function of time. We call it the error fraction because, like, if you look at the denominator, this is the difference between where the response started and where it's finally going. The numerator is the response as a function of time compared to the steady state value. So this numerator, we know that the angular velocity is always getting closer to its steady state value. So this term is shrinking, and we're just comparing that term to the numerator. And so it's getting closer. So the error fraction starts large and then it gets smaller. Let's go back to Matlab, and I want to calculate the error fraction first, and then we'll show how you can get the time constant from this. Let's go here. Okay, here's our graph again. I want to calculate the error fraction. So I'm going to go into my code. Basically, I have two pieces of data here. I have my time data and I have my angular velocity data. And I'm plotting omega as a function of time. So what I'm going to do, I'm going to estimate my steady state value, and it's around 15. Angular velocity. And let's also put our initial. I'll just call it omega naught. It started at minus 15. So our error fraction, which I called gamma, that's going to be omega. So that's a variable that I already have. It's a vector. It's a function of time. I subtract the steady state value, and then I divide by omega naught minus that steady state. So this is the error fraction. And I want to plot the error fraction as a function of time. t gamma. And let's actually put axis labels on it now. So this is time in seconds. And this is my error fraction. Oops. Error fraction. I'm going to run this. Oh, I need to make it. I'll throw another figure here. So let's put these side by side. On the left, I have my original response. And on the right, this is, oh geez. This is the error fraction. So it starts at 1. And that's the largest error we're going to have. And then it shrinks, it decays exponentially over time. My eyeballing gives you 0.62 plus or minus 0.1 for the time constant. Oh, yeah. Let's see if your guess is better. Good. So that's our error fraction. Great. Let's go back here. So we've calculated the error fraction. So to get tau out of this, if I take the natural log of both sides, so natural log e to the minus t over tau, well, you know that if you take the natural log of an exponential, it just gives the value in the exponential. So it's just going to give minus t over tau. So this is going to be equal to the natural log of, well, because we know that that exponential is equal to the error fraction. So we're going to set it equal to the natural log of the error fraction. Okay, so here's the point. Let's just write it like this. I'll rewrite this in a certain way. The natural log of the error fraction is equal to minus 1 over tau times t. So this is just a line, and this is the slope of the line. So we'll plot this and then come back to this, and you'll see how this is going to work. Let's go back to Matlab real quick. I'm going to take the natural log of the error fraction, and I'm going to plot it. And you're going to see that it should just be a line. Okay. Let's make another plot. We'll do it right after this one. Lego Logan says, I have to admit, never did it like this. Would usually just fit it with some form of error minimization and then validate on more data. Reasonable. Reasonable. No, this way is pretty nifty, and you can automate this once you've seen it once. Okay, so let's just plot. So log in Matlab is the natural log. Okay. So this is what I want to show you. You see that, okay, this initial part, yeah, let's do this. This is prior to the actual step response. But once the step response starts, the log of the error fraction is this straight line until you get to this. So this is where the noise really starts to become a problem once the error fraction becomes small. But I just want to point out, like up in this point right here, you have a pretty clear trend of the line. So let's go back here really quick. The slope of this line is minus 1 over tau. for a first order system. So here's what we're going to do. We're going to calculate slope. So we'll do a linear regression on that line. And then we know that whatever slope we get, that's minus 1 over tau. So our time constant estimate is going to be minus 1 over that slope. This is what we want to do. So I want to show you a little trick in Matlab. Let's go back. Okay, so as you guys know, or as a lot of you know, there's different ways to do a linear fit. This text might look a little small on your screen, but if you go to Tools, if you go to Basic Fitting, hello, it's popping up, it's loading. Okay, there it is. Tools, Basic Fitting. You can do a linear fit. And okay, the problem is, if I make this larger, this fits the whole range of data. So that's not something you want to do. You want to fit just this portion that actually looks like a line. And we want to exclude a good portion of this noisy stuff too. So I want to show you how to just grab quickly a truncated set of data from a data set. Let's zoom in here. I want to zoom in on this linear part. And I'm going to stop, I don't know, maybe about here, where it looks pretty much like a line. So I'm going to go from 1 second up to 2 seconds, according to the x-axis. Okay, so what if I just want to grab that data? Let's go back here. You can use the find command. Okay, so like I'll say the linear indices. So look at my data, find the indices that correspond to just that line. You can use the find command and say you provide some conditions. So t greater than 1 and t less than 2. So the find command goes through your data and it finds the indices that correspond to the conditions that you specify. So what I can do, I can go back here. That looks wrong. What looks wrong? What did I do? Tell me. Oh, T. Oh, jeez. Okay, thank you. Thank you very much. Okay, t greater than 1, t less than 2. And so what we're going to do now, nailed it, is we're going to pick only only those indices. So time at those indices and gamma at those indices. So this just calls those specific indices. Let's run this. Okay, so here is the figure. And now we see that's a nice little line. And now if I go to Tools and the Basic Fitting, I could do a linear fit, and this looks pretty good. And now's the time to compare results with Freeman, who predicted a time constant of 0.6. Oh, but plus or minus 1. You added some uncertainty to yours. That's perfect. So the slope, I don't know if you can see it. It's minus 2.034. Our time constant estimate via the error fraction method is minus 1 divided by the slope. We run that. No. It's within Freeman's uncertainty here. Okay, so it's around 0.49. And yeah, this is much better than eyeballing it. Freeman has a bionic eye. Oh my goodness. Yeah, how did you do that? This is I'm going to give you a hint here, because on the lab we ask you some discussion questions specifically saying, like, why is it that you would consider this? Freeman, should you explain? Yes, explain. Why is this method better than eyeballing it? I mean, we know this method is better, but can you put specific language as to why? I think the most important thing is we have noise in the data, and this method involves looking at a bunch of that data, fitting it with a regression that minimizes the error. So, I mean, we're fitting this with a line. Whenever you do a line of best fit, it kind of helps to average out the effect of the noise. So, whereas when I was trying to find the time constant by eye, I'm looking in a specific region where there's peaks and valleys created by the noise, and that really affects your estimate. Whereas this method, it's doing an averaging regression analysis. It kind of cuts through the noise and gives you a much more accurate estimate here. Yes. Okay, yeah, we're reaching the end of our time here, but this is the main thing that I wanted to show you today. This is something that's useful anytime you encounter a dynamic system that has a first order looking response. You can always get a decent estimate of the time constant just by eye, but if you really want to dial it in, this is a great way to do it. And it just takes a couple lines of code. Freeman says, I took a ruler and fitted it to the right side derivative of the moment of the step. The time this ruler matches the steady state line is 1 over tau. Interesting. Oh, I disabled links. Sorry. I think I see what you're saying, though. You're taking like the slope at the moment of the step, and you're seeing where that intersects the steady state line. And at least just from this little drawing I'm making, that I can see why that would be reasonable. But I'd still say with noisy data such as ours, getting that derivative is tough. Lega Logan says, isn't this a bit more complicated to prove mathematically? We're assuming a lot of things about the noise in the data and cherry picking the bit that looks most linear. Okay, let's go back. So you're saying, I mean, I'm assuming Right. Okay. I'm going to do something like if I take out the noise, well, because I had this stuff up above. Let's see what I could do. I could just suppress this. If I run this again, if you look at the error, so this is that same thing without noise. We see the error fraction starts at 0 before the step, and then once the step initializes, it's just this perfect line. Once I reintroduce the noise, let's run it again. Let's go over here. This is how it's deteriorated. So I see what you're saying. I mean, you have to decide where you think it is that the noise starts to really deteriorate the slope. But I always think even with noise, you could say like actually, what if I just fit this first little part? Like you could always fit, because I know that in theory the slope here towards the beginning should be the same later on as well. So really, I don't have to even go as far as I went. Like I could probably just go from 1 second to 1.5 seconds. So I guess my answer is it's cherry picking the part that looks most linear is not a problem, because we know that any point after that corner there should be linear. The slope is not changing. I don't know. Oh, Freeman submitted a link. Wait, let me pull it up. Oh wait, I should bring it over here first. In case you rickrolled me. So this is the technique you he did not. The slope where it intersects the steady state line is the time constant. Oh, beautiful. I hadn't heard of that technique before. That's nice. I like it. Okay, everybody. We're going to wrap it up about here. Lego Logan says, I guess I'm just wondering what happens if the noise is not Gaussian additive and zero mean when taking the log of the error function. That would... wait, I'm just turning back on some music. You're right. If the noise was not zero mean, that would throw off this whole thing. But I think that we make the assumption of zero mean error all the time. Like think of a Kalman filter. That's just a basic assumption. And I think any sensor that we're using in an experiment, hopefully it is a zero mean. You know what I mean? I think it's reasonable to assume you have a zero mean sensor in terms of its uncertainty. Have a great break, everybody. Freeman, thanks for stopping in from Germany. Lega Logan, thanks for the great comments. Tropical Geek. Can I just add a small constant instead of noise? And take a look at the graph? Let's do it. Actually, adding a constant... I don't think adding a constant will be bad. I don't think that'll affect things. Oh, wait. Oh, right. You're right. Let's see. Look at our error fraction now. Oh, because my steady state value. Oh, okay, I see. I see. So I'd have to add. Let's make it like 3. Because I'd have to add that constant here as well. If it was truly doing that everywhere. Omega. Actually, that, yeah, that's not going to be a problem. That's a good point. I mean, as long as the, yeah, zero mean isn't going to mess with it. I mean, non-zero mean. Ralph, for assignment 1, is Excel also restricted for making the tables? Or just the plot plus linear regression equation? It's okay if you use Excel just making a table to just tabulate the data. I don't mind that. Just for the analysis, I wanted you guys to practice using Matlab. Huh. Excel is heresy, everybody. That's correct. Matlab is better. Hey, thank you, Freeman. Thank you for stopping by. All right. Matlab is heresy too. I guess I do think we should be doing Python. May I ask if you know of the Knowledge Fellowship, which is a group of academic streamers on Twitch? I do know about the Knowledge Fellowship. I am on the Discord. It's just I'm not streaming as much as I was at the height of COVID. Now it's just every once in a while I'll have class on Twitch. Oh, thank you very much. Just checking, you know you are not alone. No, I think Twitch is a fantastic platform for education. Oh, Julia instead of Python. I'm not even familiar with Julia. Julia better than Python? For numerical stuff? Which is best for data science? Everyone who doesn't like language writes their own. Created in 2009 by a 4-person team. Other languages. Dynamic typing, static typing. It can call all the libraries. I'm old school and vouch for statistical software. Faster runtime. Interesting. Julia uses 1 for the first element in an array. Like Matlab. Next month, the language is going to be Jeffrey. And next, Eleanor. Yeah, it seems like there's so much coming out all the time. You can't keep up. Actually, I don't mind the 0 index. All right, everybody. I'm hungry. I'm going to have some lunch. Enjoy the rest of your day. It's been a pleasure. All right, great. See you, Tropical Geek. See you, Freeman.